Hey, welcome to my Mech 3230 project on aircraft arrestors. The goal of this project was to model a hydraulic aircraft arrestor so the system's properties could be analyzed. Some assumptions needed to be made to model this system efficiently. Assumptions included no air resistance, no self-inflicted braking from the jet. The moving pulley was represented by a single spring. Along with the Mk7 arrestor pictured here, the new AAG was roughly modeled as well to show its benefits over the older system. The first step in modeling the arrestor was to create free body diagrams of each mass involved. Equilibrium equations were used to solve for x3 double dot, x2 double dot, and x1 double dot. When starting this project, I attempted to use transfer functions to solve the model, but ran into issues after 2.5 pages of algebra. The state space model proved to be a fairly straightforward method for solving this problem. My state space matrices can be seen here in their full glory. I implemented the state space model I derived into Simulink to create plots of position, velocity, acceleration, and g-force, all versus time. Problem 1 had us find an optimal damper coefficient, Kd, for the system to arrest a 20,000 kilogram F-18 fighter jet moving at 65 meters per second. I found the damper coefficient of 3,100 Newton seconds per meter to be sufficient, although there is quite a lot of overshoot. The maximum g-force found was negative 1.023 g's, and the maximum runway used was 492 meters, both well within the acceptable range. Problem 2 had us substitute the jet with a much smaller UAV, weighing 550 kilograms and moving at 35 meters per second. As seen in the graph, the UAV will get tossed around like a paper airplane. It was found to have a maximum g-force of negative 3.53 g's and used a maximum of 38.2 meters of the runway. The Navy switched to a new arrestor system because the Mk7 was unable to handle different loads effectively. Based on the model, the UAV bounced between its maximum distances about every 5 seconds for at least 70 seconds. This is unacceptable. Problem 3 had us model the new arrestor system by replacing the Kd value with MUAV over L and vary the L to find a preferable setting for both the UAV and the jet. Through trial and error, it was found that L could be 9 times 10 to the negative 6 meters for the jet and 1 times 10 to the negative 4 meters for the drone. This means the arrestor system would at least need a range from 9 times 10 to the negative 6 meters to 1 times 10 to the negative 4 meters to handle any craft from a UAV to an F-18 jet. As seen on the next 2 slides, this new arrestor system can handle both a craft as light and slow as a UAV and as heavy and fast as an F-18.